So there's two ways we can make an ion out of an atom. We can either give it an extra electron, or we can take one away from it. And ionization energy is going to be the case where we're taking away electrons. Now, that electron can't disappear, of course, but what we're going to do is we're going to try to figure out the energy required to pull it away to such a long distance that it's like it's removed to infinity. Now, each electron that you remove is going to require more energy than the previous one. That's because now you have that imbalance. The positive charges in the nucleus no longer have enough electrons on the outside to keep it neutralized. So you're trying to pull away additional electrons. So that's going to make it much harder to take off subsequent ones. Now, here we're going to just look at the first ionization energy for the main group atoms. We're not going to worry about the transition metals quite yet. Now, as we move down, you can see that it's going to be much easier to take an electron away. Now, there's a couple reasons for that. There's shielding. There's also distance. So, hydrogen. In the case of hydrogen, we have one proton and one electron. It's going to require a large amount of energy to remove that single electron all the way from the atom. Now, that said, don't we talk about H plus a lot in chemistry? You know, acids? Absolutely. And it will take a large amount of energy to take its electron away, but not so much that it's out of bounds for us. We'll see some examples of that when we compare it to the rest of the table. But look at how easy it is to steal that electron from most of these atoms. They end up becoming very stable because as soon as you take that electron away, it's now isoelectronic with the noble gas that's right before it. So that's going to be something that is reasonably easy to do. How about our noble gases? Those are going to be very challenging to remove an electron from because, again, they are at the octet. It's going to be really difficult to break the octet up and remove an electron from it. So we're typically not going to see them ionize very easily. Now you can see that overall the trend is going to be that ionization energy increases as you come up and then increases as you come across to the right-hand side. But I'll also point out that there's a couple of speed bumps in this trend. Notice that nitrogen's higher than you expect when you're looking at it, or maybe it's oxygen's lower than you expect. And it's true the whole way down the column. You can see that there's also a similar sort of weird bump right here for beryllium to boron. So either beryllium's too high or boron's too low versus what we would expect. Now, we can explain those exceptions, and those exceptions do matter. But instead of doing it directly as a video, as like a lecture, I'm going to actually have that handled as a problem-solving video instead. Okay, also, as we come across the period, we see that it's harder to remove the electron. We mentioned that a moment ago with our trend. But there's one other thing I really want us to spot here. Look at the jump that goes from group 7 up to being a noble gas. It's hard to take an electron away from fluorine or chlorine or bromine. But it's even harder to take it away from the noble gas because you actually have to break that noble gas configuration. So it's going to be very difficult to take an electron away from one of these noble gases. Now that said, once you get down to about krypton, you're at about the same amount of energy required as it takes to take one off of hydrogen. And that's because it's going to be such a large atom then that we have a whole lot of factors at play simultaneously. For these bottom ones, we can actually knock an electron loose from it occasionally, but it's not going to be as easy to do as we think for reasons that we'll see in other videos.